Hi everybody, welcome back to the channel. In this video we're going to be talking about derivatives, which I've introduced that term a couple of times in past videos, but we haven't seen what that actually means yet. And we're going to explore in this video what is a derivative and where does it come from. In a past video we talked about an average rate of change, and so we're going to use that to kind of introduce the idea of a derivative. So an average rate of change. You may remember that from a past video, but also like from past semesters for you, this is also called the slope. I'm going to modify just a little bit. Instead of just calling it a slope, we're going to be a little more specific than that. This is going to be the slope of a secant line, which is a line that connects two different points on the graph. Okay, and we've been using m for this. And what we're going to see is that all of these kind of phrases mean the same thing. So when you hear about an average rate of change or an average speed or the slope of the secant line, those are all talking about the same thing. And you know that there's a formula for these. Okay, in your past you would have used something like y2 minus y1 over x2 minus x1. And you don't have to use y values. You could have said f of x2 minus f of x1 over x2 minus x1. I want us to look at this in just a little bit of a different way and kind of see some new notation here that's going to help us get to the idea of a derivative. So let me pull up a graph here a second. And let's say you have one point right here. We would have called this x1, and the other point we would have had a coordinate of x2. And you could look at the y values as well, but we're really just going to focus right now on the x coordinates. Okay, so x1 and x2. Instead of using x1 and x2 like we've been doing in the past, we're going to use something just a little bit different here when we jump to talking about a derivative or an instantaneous rate of change. We're not going to call it x1 and x2. Now we're just going to call it x as the first point. And then the second point we're going to talk about as, not call it x1, x2, we're going to call it x plus h. So in other words, if you look at the distance between these 2 points, the distance between those 2 points is h. All right, so the reason we'll see why we're using h here in a second, and why are we talking about the distance between those 2 points. So another way you could write this exact same formula then, instead of using y2 and y1, instead of using f of x2 and f of x1, is you could use f of x plus h, that was your second point, minus f of x, that was your first point, and then on the bottom it would be divided by, let's see, it would be x plus h minus x. Okay, which if you look at the bottom, you have x plus h minus x. The x's are actually going to cancel each other out. So an even simpler way to write this exact same thing is to say that this is f of x plus h. Create a little space in here. The graph was helpful to hopefully set up that equation, but let's go ahead and get that out of the way to have a little bit of room. So we could write this as f of x plus h minus f of x, but now on the bottom, all just divided by h. So here's another way to write exactly the same thing. Now, you might say, well, why do we have so many different ways to write the same thing? It's a good question. There's different contexts where one might be more helpful to see than the other, or one might be easier to remember than the other. But for talking about an instantaneous rate of change or derivative, this formula of f of x plus h minus f of x all over h is probably an easier one to be able to use. And hopefully you've actually seen this in your past as well. This shouldn't be something completely foreign to you also. This is something that you have seen in your past, or should have, called a difference quotient. And you probably use this when you talked about being able to evaluate functions. And can you plug stuff in correctly into a function? And the whole point there is, can you plug in x plus h into a function carefully and precisely. That's what we'll see probably actually in the next video of dealing with can you plug in f of x plus h. But this is a formula that's going to be really useful for us when we talk about an average rate of change here on out. Okay, but in this video, we're not talking about an average rate of change. We are focusing on an instantaneous rate of change. And so let's look at kind of what is the difference here. When we talk about an instantaneous rate of change, this is also called the derivative of a function, and we'll look at this in a lot of detail. Remember what we're talking about, kind of introduced this in the first video, is let's say you have a function here, and you're talking about a point, and that point has an x value. Instead of talking about the slope of a secant line, where the secant line goes through 2 points, we're going to kind of take the 2 points that we had at the beginning, and one of those points is going to kind of move towards the other point and basically become that same point. Now we're talking about finding the slope not of a secant line, but the slope of a tangent line. So when you hear the word derivative, another way to think about a derivative is that that is the slope of a tangent line for a function at a specific point that we're talking about, okay, the slope of a tangent line. And this is another way to talk about, we're talking about rates of change here. Instead of talking about an average speed, which is what an average rate of change was, you could talk about this as an instantaneous speed, and you might hear that phrase sometimes, but honestly, there's many times where we actually use the phrase instantaneous speed. Instead of using instantaneous speed, we usually just use speed. And when I talk about how fast you're going, you don't usually assume that you're thinking about over a long time period as an average speed. Usually think about, kind of interpret that question as me saying, how fast are you going right now? And that's your instantaneous speed. Or another word for speed is the word velocity. And so again, all of these words or phrases mean exactly the same thing. I say this because you might see one problem in your book that says, what's the instantaneous rate of change? The very next problem will say, what's the speed? The next problem will say, what's the derivative? The next problem will say, what's the slope of the tangent line? All of those are asking exactly the same question. Okay, and there's actually only one change that we're going to make to the formulas that we had in the last page talking about an average rate of change, is that now this is going to talk about we're still going to have exactly the same thing, f of x plus h minus f of x all divided by h. But now, instead, remember what h was. H is talking about the distance between 2 points. And so that second point, if you remember what was happening with that second point, it's getting closer and closer and closer to the first point. So we're basically turning those 2 points into exactly the same point. The distance between them is getting so small. So the only difference now, the only change when we talk about an instantaneous rate of change instead of an average rate of change is that we are going to take the limit as h goes to 0. Okay, let's let h get really small so that the 2 points basically become the same point, and so that's the formula that we want as far as being able to find an instantaneous rate of change or a derivative. Okay, now this is going to be true in general. We're going to see that you can do this for a lot of different values or a whole entire function even. But for now, we're going to look at just doing this for one specific point, at a very specific point on the graph first. So for now, for this section, it's probably better for me to write, instead of f of x, it's probably better for me to write that the limit as h goes to 0 of f of a plus h minus f of a all divided by h, where then on the graph, instead of talking about x being a variable that takes on a lot of different values, we're looking at one specific value of a, saying, what is the slope of the tangent line at exactly this point right here, at exactly a? Okay, so remember from the first video, a slope of a line like this is talking about a speed that has the units of distance divided by time. Okay, and we are not looking over an interval now, we're looking at one specific value of a. By the way, it is actually possible to kind of approximate this, uh, the slope of the tangent line here. Like if I knew that A was, let's say 2, and I could try to find, I'd probably have to eyeball this. This is probably a something where, like, if you had a ruler or a straight edge and kind of could draw a really good tangent line there that says, which this is clearly not, but if you could draw a really good tangent line there, and if you could say, hey, could I try to find another point on that line, okay, and probably try to estimate that. So maybe here's a point that's on the line. By the way, that point is not on the curve, but it's on the tangent line right there. And if you could find another point on that line, then you could actually calculate the slope of that tangent line, or at least estimate the slope of that tangent line by kind of eyeballing where there's another point over here, and by using your y2 minus y1 over x2 minus x1 by finding the slope of that line the way that you normally would have done it. That's a little bit sloppy because you need to kind of eyeball this line and try to find what you think is another point on the line. In the next video, we're actually going to see how to be able to do that a little bit more algebraically and more precisely, but you could try to do that by kind of using a graph as well. It's just a little bit more arduous and a little tedious. Okay, in the next video, we're going to take a look at a lot of examples about how to calculate a derivative at a specific point, as well as how to calculate a derivative using pretty much any point on a graph. And we're going to do that a little bit more algebraically, which is going to be more precise, more accurate, and a bit easier, to be honest, than trying to just eyeball something on a graph. Okay, so check out that video. Good luck practicing.